Hi everyone, welcome to System Design Expert, and this is new video where we are going to learn into system architecture or backend architecture of a coding contest platform like Leetcode. There are a bunch of those such as HackerRank, CodeChef, Codeforces, Leetcode. So these are platforms where user are able to read the problem statement, and for that problem statement they write a solution in specified language and submit the solution, and the online judge takes the submission from the user and figures out for all the hidden test cases as well as the test cases that are on the console, if they are working as expected. If yes, you get all clear. If not, you either get some penalty on some platforms or you do not get any penalty in terms of final output. This is the problem statement we are looking into. Without wasting time, let's jump into the agenda for the video. So agenda is pretty simple. We are going to have a requirement gathering phase. We are going to discuss which kind of designs, APIs that are going to be there as a part of our core problem design which we are looking into, and then we look into component design, and finally deep dive for each of the component. First, the requirements. What would be the requirements? We are focusing more on the contest like environment instead of question banks. So here we are trying to focus on having those 90-minute contest where user will look into the join the contest. For that contest, let's say there are three or four problems. For the each of the problem, it is going to submit the solution, and against that timeline, after 90 minutes, users will be able to see their rank on the leaderboard. So this is more of platform we are looking into. So basically, users should be able to join the contest. We are assuming it is going to be 90-minute contest, similar to what we have on Leetcode. Check leaderboard after contest completion. This is again can be extended to real-time leaderboard as well. But for the sake of this problem, we are looking into leaderboard only after contest is finished. For some other video, we can look into real-time leaderboard. Then user should be able to run code against input test cases. So those input test cases can be provided either by the user or can be fetched from the input file, where we have lots of input files created against which we need to match the output, and user should be able to submit the code saying that, hey, this is the submission for my problem, please evaluate against hidden test cases and all. This is what user should be able to do with the platform. And platform, as a Leetcode platform, you should be able to test the code against the set of inputs. So we assume there will be multiple hidden test cases, and those test cases should be tested against the code submitted by the user. So these are the requirements we are looking into. Let's look into some estimates. Through estimates, we do some sort of number crunching in order to understand active users, concurrent request, bandwidth utilization, memory utilization, etc. So here we are assuming 20K as a participants for each of the contests. For each of the contests, this number is being taken from the Leetcode stats, where for weekly and bi-weekly contests, around 20 to 25K is the max candidate pool that they observe, with each solution size being around 2 KB. By 2 KB, it implies we have around 2000 characters present in the solution. That is more than sufficient for an average use case. Each submission takes around 5 seconds to execute. Either we can keep it as synchronous or we can keep it as asynchronous. Because its submission needs to run against multiple hidden test cases, we assume it is going to take some time, because there would be some concurrent request as well. So assuming 5 seconds is a pretty good starting point. Now let's compute a number of executions per second that are running concurrently. So for this, we assume 5 into submissions per second. Why 5? 5 is the submission, each submission going to take time against the all the input files. So that is 5, and into submissions per second. We assume there are 20K active candidates, so 5 into 20K. Okay, then the six as a factor comes in, where we assume that for each set of problems, so let's say there are 3 or 4 problems in the contest, there are on an average six submissions provided by each user. So this can vary based on, some users may submit on the first problem, or they may go for all 4 problems. There will be some wrong answers during the journey, so we can assume for each user number of submissions are going to be 6 divided by 90. 90 is the contest duration, so 90 into 60 to convert minutes into seconds. This comes around 111. Of course, these are dependent on the assumptions of 20K, 6 submissions, 5 seconds to execute, and 90 minutes of contest time. We can, always tweak these parameters to get concurrent executions per second parameter. For the starting point, 111 is a pretty good start. For actual Leetcode contest, this numbers comes around 50 or 55. So 111 is pretty good scale with which we're looking to design the system. If we have 111 concurrent executions per second, we can assume that for octa-core machine, that is, it is going to have the 8 threads basically, so it can, concurrently run 8 different programs. So for octa-core machines, total number of machines required to execute the submissions provided by the user is going to be around 15. So 15 into 8 come close to 111. So yeah, this is about estimates. Let's look into required APIs for the platform. First sort of, pretty simple API for a specific contest, get all the problem statements for specific problem ID. Let's say ID 111 is part of contest 1. For that ID, get me all the description of problem. What are the problem statement? If there is any metadata, there might be some explanatory images, sample test cases, those kind of stuff. So for each problem statement, get me all the metadata for the same. This is one API. Two APIs we need to have in the system. One for contest, get all the problems, and for each problem ID, get me all the problem description. Then we have submit API to execute code against hidden test cases. And then we have get result of executed code for the problem. So the submit API can either be synchronous or asynchronous. By synchronous, we mean if I submit the solution, I will get the result of that code execution immediately. Not immediately, but with the same network call. So my submit API input is my code and problem ID, and output is the what's the output for the code. If it is passing all the test cases, what is the memory usage, time constraint, etc., or the wrong answer, all the stuff will be provided as a response to the submit API. It is going to hold a 5-second network call before sending out the response. And this is the way if we do execute the submit API in synchronous way. However, it is not the most efficient way to go for this approach. Reason being, we're holding a network resource, network bandwidth, all the connection thread, all those stuff for the entire 5 seconds in a blocking state, and we definitely don't want to have that. That is why there is asynchronous way of executing this problem. With this, we have a couple of approaches: polling, WebSocket, server-sent event. Let's look into each of this. Let's move to whiteboard, and we would like to see how polling work against the, like how polling solution can be implemented, how WebSocket solution can be implemented for the problem, and how server-sent event can be executed for the problem. Let's jump into Scalability. Okay, so I hope this is visible. So here we have all the 3 solutions and some of the hypothetical way of looking into this problem. So in polling, what we create is, what we do is we do a submit call, submit API call, saying that, hey, this is the code against this problem statement, create a task against it. So backend execution service creates a task saying this is the task ID, and this task is in progress or not started, or will be started in the future. That sort of specific response will be sent out to this submit API, saying that, hey, this is the 202 HTTP status. We received the input and will process it in the future. Now, after each X seconds, let's say X is 5 for the sake of understanding. Let's say we created a task at a time equal to T. Now, after T plus 5 seconds, front end is going to ask the backend saying that, hey, what is the status of this task ID which I received? Is it complete? Backend will check if the task is complete. If yes, it is going to send out, hey, this is the result. If not, it is going to send out, this task is still in progress. Now, after plus, let's say again T plus 10 seconds, because X is 5. So T plus 5, we got in progress. Let's say at T plus 10 as well, we got in progress. Now, let's say at T plus 15, backend execution mentioned that, hey, this execution has been completed, and this is the result. Whether it is all clear, like submission is passed, the task is successfully complete, it is not complete. So that complete result is going to get back to the browser. If you want to know how Leetcode does this, Leetcode does the exact same thing. So polling is a solution which they currently implement. Let me show you with a real example. So this is a problem statement to some problem basically. If I hit the submit API, the submit API call goes to the backend. It goes to Leetcode to some /submit. The payload is this. We get the response saying that, hey, this is the submission ID. Now, after each 1 second, the Leetcode frontend, the browser is calling this check API. Leetcode.com/submission/details/submission ID/check. And this check call is going against fixed time interval, and it is going to, let's see what we get in the response. It's getting still pending, pending, started. We got started here, and in next check call, we got to know that this execution has been completed, and what is the result, if it is passing or failing. Based on that, we get the response back. This is one way of executing the asynchronous way of submitting the task and getting to know about response. Second way of doing this is WebSocket. As we discussed in previous video as well, WebSocket is by-way communication platform, by-way communication protocol through which server can send information to client can send information to server without recreating the three-way handshake and sending headers every single time. So for a WebSocket, what it is going to do, it is going to submit. So this is the submit task. It is going to the backend execution is going to get the task ID, and it is going to say acknowledge, hey, your request has been acknowledged. That's it. It is not going to, like, browser is not going to ask back to backend execution saying, hey, what's the status for this. Instead, backend execution is going to finish this task in asynchronous manner, and once it finishes the task, the backend is going to send out the result. Okay, hey, this is completed, and this is the result. If it is passed or failed. So response after execution is completed, it is going back to the user saying that what's the status, like this is the result of the task ID. Of course, WebSocket, with WebSocket, there comes a lot of complexities. By complexities, we imply that WebSocket needs to be stateful in a way. Scaling of a backend execution service is going to be a little trickier than what used to be for polling or any other solution. So WebSocket can be used for use cases where there is a lot of frequency of message going back from server to client. Yeah, this is where WebSocket is being used. For this solution, for the Leetcode kind of platform, where for the submit and getting the status back asynchronously is a kind of little too much. So between WebSocket, because WebSocket, again, it comes with its own difficulty maintaining the WebSocket of each device, its socket, what is the task ID against it, all the stuff needs to be maintained manually for the by the backend execution service. So this is where WebSocket comes at little too much for this task. And then we have third option named SSE, that is server sent events. Here we are going to rely on a specific property of JavaScript running in the browser. So JavaScript, if you might know, is able to listen to certain events. So from the front end perspective, it can be, on click, on key pressed, on mouse over, on close. So those kind of events are being generated most of the times through user and interaction, and JavaScript is able to listen to those events through those similar to those events. Yeah, same front end JavaScript is able to listen to events generated by the backend service. Those are known as server sent events. So for that, front end explicitly, like browser explicitly needs to subscribe to specific event so that it knows when the event is published. A simple observer pattern, design pattern is used. Probably in the future we can discuss more on that front, but basically observer pattern is used when we want, like a client wants to know update of after want to know any update that is being reached by some server or by some other client. So this is where server sent event comes into picture. It's inherently depends on JavaScript's or browser's ability to listen to certain events. So here how the flow goes is it sends out the task ID. Okay, it sends out the submit task. It is going to create a task ID. It is going to send the acknowledgement and the events. Okay, so we are going to get acknowledgement and event ID. So what this event ID is going to do is, for this event ID, browser needs to subscribe to this specific event. So it gets the event ID, it subscribes to the front end, subscribes to that event, and then once this backend execution finishes asynchronously, the backend service is going to trigger the SSE, and that SSE is going to be listened by this front end, and that's how front end is going to know that what's the status of my updated, what's the updated status of task I submitted some times ago. So this is how server sent event comes into picture. If you ask me, server sent events are, through polling, there are some disadvantages where we are continuously choking down the backend service with constant updates saying that, hey, what's the status now, what's the status now, what's the status now. And most of the times, as even you might have noticed here, we got multiple check with same status known as pending. So there is a lot of bandwidth wastage in that approach. Then we have WebSocket. Through WebSocket, we can see that there is a lot of complexity comes into picture for scalability purpose. And then there is server sent event that lies between it brings out really good balance between complexity and easiness of implementation. If you would ask me at this point, if we would like to redesign the Leetcode from scratch, we would have gone with the server sent events instead of relying on the polling part, and obviously not the WebSocket part. So yeah, this is what I would like to discuss in detail before going into actual architecture. Let's go back to the slides and see what else we have. So these are three APIs, and then we have one more API for leaderboard to figure out what's the who are the top 10 users, 5 users, and what is the my current rank, like things like that. So we are handling the leaderboard as a post-processing job instead of keeping it real time for this design. So yeah, with this, let's jump into whiteboard, how we are going to design this system. Let me draw a line saying that, hey, this is our starting point. Awesome. Now, to start with, let's create scenarios through which user can interact with the uh, backend architecture. So this is browser. reading problem. Okay, this is one use case. Second use case being browser submitting solution. Okay, and now third event would be leaderboard. Browser checking leaderboard. All right, with this, we can start with the API gateway. Okay. There's subtle difference between when to use API gateway versus when to use load balancer. I seen most of the folks in the interview use API gateway and load balancer alternatively, interchangeably, but that's not the case. Each of them have their own purpose. Probably API gateway is superset of load balancer. In short, okay, we can have this discussion in separate video when to use what. Okay, awesome. Now let's toss all the let's go with the first use case. For the first use case where uh, browser reading problem. We have problem serving service. Okay. Uh, let's have this medium text. Awesome. So with this, what we are going to have? Wait, problem serving service is going to have its own database. Let's have a problem metadata DB. I'll let you know why we are writing problem metadata DB and what are the contents in this database. So we have problem metadata DB. We are going to store the static information such as, all the problem description, the problem image, if there is any for the specific problem, into separate object storage. So let's call it as problem description object storage. Okay, so this is object storage. Probably in terms of AWS, it is S3, similar to S3, of course, Azure and other cloud platforms like Google Cloud, OCI. They are going to have their own solution, but yeah, S3 is kind of a industry-wide known thing for its reliability and availability purpose. So yeah, we're going to store problem metadata and we're going to store actual description images in this object storage. Okay, so one more thing, one more component we're going to have is CDN basically. Okay, so this is again we're going to have push based CDN. We can discuss pull based versus push based CDN in some separate video. But push based CDN is going to be used for this approach so that user, whoever trying to read the problem, does not need to look into file storage to read the problem. It can be fetched directly through CDN. So like example of CDN would be Cloudflare, which is used across the industry. Let me draw a user request. So user comes in, tries to, say, I want to read contest one, problem with ID one. Problem serving service is going to look up into problem metadata, and it is going to return out, the response saying that, hey, the text and other description is present in this S3 URL bucket. It is going to go back to the user saying that what is the metadata of problem, and then again user is going to call to CDN in order to get the actual content of the problem. If you want to know how Leetcode does, let me open the design here, problem here. If you see, this is problem present from, let me close this. This is weekly contest 361, happened on 3rd of September. If I do inspect, oh, sorry. If I open this problem and do inspect, go on network tab, see how things go. There are multiple GraphQL APIs. Enable code. Let's see where this question description operation goes. Question title, question content. Yeah. So if you see this in the question content, we see that the server is Cloudflare. It is not leetcode.com or leetcode.cl, but it is Cloudflare. It implies that Leetcode is relying on this CDN to serve the actual content. If you see the response, content is there is undirected tree with en nodes labeled from something. So this is the same exact description. So yeah, this is how Leetcode does it as well. So it relies on the CDN for the providing the content part. So this is how problem seeing use case looks like. Next, we are going to look into problem submission task. So let's say this is submission server. Okay, so submission server is going to take the input. As we discussed previously, let's say it relies on server sent events. Okay, it can be again WebSocket based or polling based, but for now, for this implementation, let's take the WebSocket. Let's take the SSE approach. So, what is how the user journey looks like? So first, the request comes to the request, like all the code, actual code created by the user comes to submission service. Now the submission service, what it does is, first thing, it uploads the code to some file storage. Given it is code, text-based information, we do not need it directly stored in the some sort of database. So let's say we have code submitted into bracket S3. It is again object storage, nothing specific to AWS. We can assume similar services are there for the different cloud providers. So this is two. Once it does that, we do not, instead of doing all the tasks synchronously, what we'd like to do is we'd like to push the event into some queue, saying that check out the submission, check out the code added by the user ID. Okay, now this is third. And once the event is published to this broker, response goes back saying that, your request is being received properly, and we're going to give you the response with this event, okay, to which you can subscribe to. So let's call it as code submitted event queue. It's basically equivalent to file-based queue, similar to Kafka, or for AWS, we can rely on SQS instead of Kinesis. Yeah, SQS is again a very good option. Similar to that, we have available services in the other cloud providers. So we have code submitted queue. Now this code needs to be executed against the very controlled environment. If you would like to discuss this, this code needs to have certain constraints, such as time constraint, such as space constraint, and these constraints needs to be validated. Usually for such kind of information, in the older times or in the previous times, the code containerization kind of scenario was used. something like that is provided readily by Docker. We can create multiple containerization for each task, and against that task the user submitted code used to be run against. Reason being, we do not want to run the process directly on bare metal or directly on the process run by the Leetcode backend. Basically, if user sends some malicious code, the malicious inject file can run into our server and can cause the heavy X. So instead of giving complete access to the process that is run on Leetcode backend or the backend of platform which we are building, we just provide the containerized environment. So usually in older times or in previous times, containerization used to be go-to solution for this. But with recent advent, we can directly rely on something known as serverless functions. Okay, we can directly rely on serverless functions. Example being AWS Lambda, that is provided by AWS cloud ecosystem. Again, equivalent would be there. So these serverless functions can have really good profiling information. By profiling, we mean to us, it can fetch what is the executed time, more accurately, what was the memory used, what was the constraint, and it can be dynamically created against multiple languages. So let's say user submitted code against Java, against C++. For containerization, it needs to have the JVM or CPP compiler. But for AWS, for serverless functions like Lambda, it is very easy to manage this through the code. So again, both of them are equally good solution, but with Lambda, this own manage ecosystem we do not have to rely on. We do not have to worry about creation of new Docker containers, management of Docker containers, their life cycle. The AWS Lambda or serverless functions are going to take care of this thing. So we can say serverless, not serverless, we can say code executors, code executor workers. So this is equivalent to serverless function. It fetches the information asynchronously. It fetches the user ID, problem statement, and it gets the S3 URL, the code submitted URL. It is going to fetch this value. Okay, so I am going to have an arrow like this to fetch the code. It again needs to fetch all the problem statement, all the input and expected output file, right? For each problem, it needs to run against set of input and output file. So we can have this in a separate S3 bucket. We can call it problem input output expected output bucket storage. Okay. It fetches this value as well. And now against the code, against the input output file, it executes the information saying that, hey, for this user, this is the value and response. Now, once the execution is complete, we would like to store this information somewhere. Okay. So we are going to store this value in a database, like let's call it user submission DB. Okay. So user submission DB is going to store the response of my bad is going to store the response of code execution. And once this response is stored, the code executor workers are going to call the submission server, saying that, hey, for this specific task ID, this is the result. This is the result of code executors. Again, this communication can be either API based or can be decoupled, and again, a new queue similar to this queue can be added for communication between code executor to submission server. Once it has this information, it is going to notify the browser with the server sent event, uh, saying that, hey, this is the this is fifth. This is the output against the task ID. So yeah, this is how entire flow of code execution looks like. We get the request, and this is one. The second, we store this in S3. From that S3, once it is stored in S3, we create an event and push it in against the message queue, saying that code submitted event has been created, and we get back to user saying that, hey, don't worry, your task is received to us with 202 HTTP request, and you will be notified with this event ID. Please subscribe to it. Asynchronously, whatever event is added to the queue is being taken through the code executor worker. Code executor worker takes on input file, takes on code submitted. It executes in very constrained form, saying, we need to execute in 1 second or 2 seconds. This is the limited memory that we got for 4 MB, 10 MB, whatever platform decides. And once it executes the code, once it compares output and expected output file, it stores the result in user submission DB. Once it stores the user submission DB, it notifies the submission server saying that task computation is done. Submission server go back to creates an event SSE that the browser gets to know about, and this information is received to the browser somehow, this way. This is how entire journey of problem execution in containerized or serverless environment looks like. Now we have one more use case. Let me zoom a little bit. Now we have browser checking dashboard. Sorry, yeah, leaderboard as a use case. Now what we have is we have user submission DB here. Now for this DB, from this DB, we need to create the leaderboard. Now let's look at how leaderboard service looks like. So whatever information being added, saying that for this user, for this task, this is the result. And now it is going to run a basic map reduce job. Okay, map reduce leaderboard job. So what it is, simple map reduce job can be executed through Spark, can be enabled through Spark. What it is going to do is, it needs to, let me write it down. What it needs to do is, first, for each user from a problem, for each user, get submission, get accepted solution problem wise. Okay, for each user, for each problem, get me the time, get first accepted solution time. Okay, so here we are trying to look into time. So for this is the earliest time at which user has submitted the correct solution. Now for each user, get count of wrong answer, before getting correct answer. Now this is the second thing it is going to do. Okay, after this, what needs to be done? It needs to, this is the map job, basically map this, map first step, map second step. It is going to find score of each user problem wise. Okay, This is the third step. It is basically going to be the reduce step. Sort score sum of scores. Sort sum of scores. And this is the final step where we are going to again do the reduce job to get the sorted order of the task. This result is going to be stored in separate database. Let me add a DB here. Okay, so this is leaderboard DB. For each leaderboard query, we have leaderboard server to serve that request. Leaderboard server. All right. So whatever request comes to leaderboard service, it fetches the leaderboard. It queries the leaderboard. Basically, leaderboard service is going to query the leaderboard and responding back to the user. It's a very simple implementation of leaderboard service. Had this been online, we would have need to rely on stream processing to process the events in near real time. But since we are more focused on containerized code execution, which is which lies in very core part of things like for the platforms like Leetcode or HackerRank or CodeShape, we had more discussion on that front. Yeah. I think this is a very solid design for this problem statement. Let me write down the schema for each of the database that we have considered. Okay. So first we have problem metadata DB. Okay. Let me minimize this. So for problem metadata DB, the information that we are going to have is contest ID, problem ID, maybe problem title, and the problem description URL. So this URL would be of S3 from where it can fetch the problem statement. Okay, now this is the problem metadata. We don't see any complex joins going to come into picture, or we don't see any complex queries that we're going to do. A simple contest ID and problem ID are the queries through which the query pattern looks like. So from that, we can simply use any key value based database. AWS, if you have AWS platform, DynamoDB would be good starting point. Obviously, DynamoDB gives other sort of way through which you can query the data, but for our use case, plain contest ID and problem ID query pattern is more than sufficient. So we're going to have partition key on this, and we're going to have sort key on this. Okay. So this is how problem metadata looks like. Problem metadata DB looks like. What else do we need? We need user submission DB. Let me write it down here. User submission DB. What data patterns do we have? We are going to have user ID, problem ID, and we are going to have submission code, submission URL. Yep, this looks good. Again, similar to problem metadata, we can rely on a DynamoDB sort of database, key value based database for this as well. And for leaderboard, we can simply have contest ID. Oh, wait a second. For user submission DB, we have this map reduce. If you remember correctly, we have this map reduce dependency. And as far as I know, DynamoDB do not readily support the map reduce task or any directly Spark based map reduce worker environment. So for that, probably we may need to switch this to Cassandra for that matter, because we would like to store one more value here. If you think about it, we need to store the result as well. So result, this result can be complex object with a dynamic number of columns. If the result is negative, that is it is wrong answer, then result can simply say a wrong answer. If result is correct, then we have dynamic columns such as memory used, time used, the time submitted, all those stuff that is related to the execution part, language used, all the stuff, right? So for that matter, we can have dynamic number of columns, and it directly supports Spark MapReduce job as well. Because of these reasons, it would be better for us if we rely on Cassandra table here. So Cassandra table. If you want to know more about which database to use when, we can have a separate video on that as well. So we have MapReduce leaderboard job. We have leaderboard DB where we simply have contest ID. Wait, we have contest ID, and then we have user ID, and we have the rank. Problem wise info. This would be complex JSON object where for each problem we can have submission score, like for this problem, what was the score scored by the user, and we have actual rank. So leaderboard DB looks quite solid in that way. It is going to serve all the user request. So yeah, for leaderboard, we can again consider Cassandra based on dynamic number of columns that will be part of the schema. So yeah, I guess that's pretty much solid design we have covered. Let me see if anything is missing. We have CDN, we have API gateway, we have all the user journey through which data value has been stored. We have code submitted S3, and we have leaderboard map reduced job, and we have their steps against map and reduced. I guess that's pretty much from the design perspective. Thank you very much for joining this call. In the future, if you want to know more about some other problems, do let me know. We're going to have multiple such discussions. Hope you have enjoyed this discussion. Thank you.